Welcome to this lecture series in real analysis. In this lecture, we'll discuss the Cantor-Shroeder-Bernstein theorem, which is a fundamental theorem in set theory. It has nothing to do with real analysis. What does it say? It says that suppose we have two non-empty sets A and B, and suppose that there is an injection from A to B, and there is an injection from B to A. Then there is a bijection from A to B. It's a very, very fundamental and interesting theorem. So to show that two sets are in bijection, you need not work very hard. Just construct an injection from A to B, construct an injection from B to A, and that's it. Therefore there exists a bijection between A and B. And that makes life a lot more easier than it would be otherwise. An equivalent formulation of the theorem is in terms of surjections. So here we have two non-empty sets A and B, and if there is a surjection from A to B and a surjection from B to A, then also there is a bijection from A to B. Going from one theorem to one version to the another is very simple, because having a surjection from A to B implies that we have an injection from B to A, and similarly for this direction. So the equivalence of these two statements is clear. And before we discuss the proof, let's talk about a small notation. So if there is an injection from A to B, we write this. So the theorem says that if this happens and that happens, which is same as saying that if there is an injection from A to B and an injection from B to A, there is a bijection from A to B. So when we write this, we mean that there is a bijection from A to B. So the symbol is read as cardinality. And if you put some set inside it, you say cardinality of A. And this theorem says that if cardinality of A is less than equal to the cardinality of B, which we have defined what that means, it means that there is an injection from A to B. And if the converse also happens, then equality happens. So this is a very, very good notation. It is very easy to remember things in this notation. Remember that these are not numbers, but still we are defining a comparison between them. Okay, so we will not be discussing a very, very formal proof of it. In fact, I encourage that you skip the proof. For the first reading, my recommendation would be to just skip the proof and take this theorem for granted. But if you insist on seeing a proof, let me get there. So the proof that I like is due to Conway and Doyle. I will not be discussing it in full detail. We will be using graph theoretic terminology, and you can consult the videos in the playlist Kickstart on graph theory. Those videos pertain to mainly finite graphs, but here we will be dealing with infinite graphs. Okay, and I will hopefully not forget to put links to other proofs in the description. Since this proof will not be entirely detailed, I feel obligated to give references to outside sources. Okay, so let's see what is the main ideas. What are the main ideas? So let's start with injections. F is an injection from A to B, G is an injection from B to A. And what we will do is we will define a bipartite graph on two sets. So the left side of the bipartite graph will be all the elements in A, and the right side is all the elements in B. And let us now define how to join edges between a vertex in A and a vertex in B. So we join an edge between A and B if either FA is equal to B or logical or GB is equal to A. So this is how we draw the edges. Okay. So yeah, now note that every vertex in this graph, either from A or from B, has this constraint. The degree is at least 1 and it cannot be more than 2. Why is that? Why degree at least 1? Because you pick a vertex from A, it is mapping to something, and therefore it has to have some edge. All right, and it cannot have more than 2 edges, because if it has, let's say, more than 2 edges, let's say it has 3 edges, then one edge could be due to A mapping to something. Well, one edge has to come from there. But then the other 2 edges have to come from G mapping these 2 points to A. But then G wouldn't be injective. So no vertex can have more than 2 edges. And 2 edges happen precisely when you have B mapping to A and A mapping to some. I mean, in this picture, if suppose you have 2 edges, then either it could be due to B mapping to A and A mapping to this guy, or this guy mapping to A under G and A mapping to B under F. Okay, and now there are 3 kinds of, or maybe more than 3 kinds of, there are essentially 3 kinds of components in this graph. You could have infinite paths. Infinite paths further can be of 3 kinds: both way infinite, or one way infinite, meaning it could be something like this or that, or you could have finite paths, or you could have cycles. There are 3 kinds of components in this graph. Why is that? Because this is because of this reason. And this is very easy to see in finite graphs. In fact, in finite graphs, you cannot have this situation. You can only have finite paths and cycles as components. That is very easy to see. But since our graph is potentially infinite, in fact, it could be uncountably infinite, this extra case occurs, which, as we said, further could have extra cases in it. But in each of these components, so if we had this component, we can easily look at a bijection. I mean, from this portion to that portion, we can construct a bijection, because it could be something like that. Sorry, so just map this to this, this to this, this to this, this to this, and this to that. So that would be one way to get a bijection from this part to that part. And similarly for cycles. And you can also think about infinite paths. So this part of the proof that I'm discussing is a little bit sketchy. And I don't want to give too many details here. But basically this is the idea. This is the main idea of this proof by Conway and Doyle. Okay, but as I said, I encourage you to skip the proof of this theorem for now. Not because this proof is too hard or anything. It's just that it's my recommendation that it will make you learn things faster. Some things should be skipped, and this is one of them. Okay, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.